Imagine you're trying to study for like the most important exam of your entire life.
Okay, I'm picturing it. High stress.
Very high stress. And you have this massive 1,000-page textbook sitting right in front of you. But there's a catch. A really bizarre, frustrating rule you have to follow while you study.
There's always a catch.
Right. So as you read, you are absolutely not allowed to flip back to page 20 to, review a specific formula. You can't go back to chapter 4 to check a definition you forgot.
Oh, that sounds awful.
It gets worse. Instead, every time you turn a page, the book forces you to read this heavily blurred, tightly compressed, single paragraph summary of every single chapter you've read up to that point.
Just a single paragraph for hundreds of pages of text.
Exactly. If you're on page 900 and you need one tiny, highly specific piece of information from page 10, you are out of luck. You just have to squint at this muddy, chaotic summary and basically guess.
I mean, that sounds like an absolute nightmare for learning. You would spend all your energy just trying to decipher the summary instead of actually processing the new information right in front of you.
Exactly. But the thing is, and if you are listening to this right now, you really need to understand something staggering here. That nightmare scenario is exactly what we are forcing our most advanced trillion-parameter artificial intelligence models to do. Every single time they process a prompt.
We are essentially crippling them, yeah. With an architecture that intentionally blurs their own internal logic.
It's wild to think about. I mean, it's a phenomenal analogy, and it cuts right to the heart of what we are unpacking today. For years, we've kind of treated the internal architecture of large language models as this pristine, highly optimized machine.
Right. We look at the block diagrams, we see the neat sequential layers, and we assume it's the absolute pinnacle of engineering.
But the reality, when you actually look at the mathematical flow of information deep inside these networks, is that the architecture is incredibly muddy. Crucial insights generated by the model's early layers are literally just being buried under a mountain of mathematical noise.
Welcome back, the listeners, to the Neural Intel podcast. Today, we are taking a deep dive into a brand new, highly technical, and frankly revolutionary report from the Kimi team.
It's titled simply, Attention Residuals.
Attention Residuals. And as always on this show, our mission is to cut straight through the industry hype. We're going to focus strictly on the technical details, the math, and the distributed systems engineering that makes all this possible.
We really want to break down exactly how information flows through the actual layers of a transformer and, why changing that flow unlocks such incredible gains in reasoning.
And to stay updated on the latest in AI and ML, visit our blog at neuralintel.org and check us out on YouTube, Apple Podcast, and Spotify. And please, we really want to hear from you. Always give your take in the comments below. We read every single one. There is just an immense amount of ground to cover with this Kimi team report today, from theoretical math to pure hardware optimization.
So before we really start turning the gears and getting into the weeds, I want to clearly lay out the framework for today's deep dive. We always want to know what we are solving. The hook here is a terrifying question for AI researchers. What if the very architecture that allowed large language models to scale up to billions of parameters in the first place
is the exact same architecture that is burying the most crucial information your model learns?
Exactly. And that leads directly to the core problem we're investigating today.
Right. It's a phenomenon called pre-norm dilution, which happens within standard residual accumulation. Essentially, as a model gets deeper, the mathematical size of its hidden state grows linearly.
Like an O of L growth curve, right?
Yes, exactly. And this uncontrolled growth progressively dilutes the contribution of each new layer. It acts exactly like an outdated recurrent neural network, or RNN.
Because it traps early insights so they can't be selectively retrieved by the deeper layers.
Precisely.
Which brings us to the solution the Kimi team has engineered here. Attention Residuals, or AttnRes, and its highly optimized variant, Block AttnRes. By replacing fixed dumb addition with a learned dynamic softmax attention mechanism over previous layers, the network can selectively retrieve exactly what it needs from its past.
We're talking about completing the transition from rigid, fixed routing to dynamic, intelligent routing. But importantly, we are doing this across the depth of the neural network rather than just across the sequence of words.
Okay, let's start tearing this down. If you're listening to this and wondering why we even have this problem to begin with, we need to talk about the standard residual connection.
The absolute foundation of modern deep learning.
Right. If you look at the PyTorch or JAX code for literally any modern LLM GPT-4, Llama 3, DeepSeek, you will find this equation everywhere. H sub L equals H sub L minus 1 plus F sub L minus 1 of H sub L minus 1.
It is arguably the most important single equation in modern AI. The current hidden state, which is H sub L, is equal to the previous hidden state, plus whatever complex, nonlinear transformation the previous layer just performed on that state.
And that simple plus sign right in the middle, that is the residual connection.
Exactly.
But why was that plus sign such a big deal? I mean, why couldn't we just pass the data through the transformation and, move on to the next layer? Why add it back to the original?
To understand that, you have to look back at the dark ages of deep learning, like before 2015 when ResNets were introduced. Back then, if you tried to build a neural network with, say, 50 layers, it simply would not train. It was mathematically impossible.
Because of the vanishing gradient problem.
Right. When a neural network learns, it relies on gradients. You give it an input, it makes a guess, you calculate the error of that guess, and then you send a learning signal, the gradient flowing backward through the network. From the final output all the way to the first layer, this is backpropagation.
And the network uses this signal to adjust its weights so it gets smarter next time.
Yes. But every time that signal passes backward through a standard layer, it gets multiplied by various weights and passes through activation functions like ReLU or TON.
And if those weights are small, or if the activation function squashes the numbers, that learning signal just gets multiplied by a fraction.
Exactly. Multiply a fraction by a fraction 50 times and you hit 0. The signal vanishes. The early layers of your network never receive any feedback, so they never learn anything at all. The network effectively flatlines.
So the residual connection was introduced as like a bypass.
A gradient highway, yes. By simply adding the original input back to the output of the transformation, that plus sign, you create a literal identity mapping. You are providing a paved, unobstructed highway for the gradient to flow backward through the entire depth of the network without being squashed by the transformations.
Oh, so the transformations just learn the residual, the difference, rather than trying to learn the whole mapping from scratch.
Right. This single trick allowed us to scale from 20 layers to hundreds of layers, giving birth to the deep learning era we're in now.
It's a brilliant hack, but the Kimi team paper points out that this hack, specifically the way it's implemented in modern transformers, has created a monster. They call it pre-norm dilution.
Yeah, and to grasp that, we need to understand pre-norm.
Right. Walk us through what pre-norm actually means in this context, because there used to be a big debate between post-norm and pre-norm, didn't there?
There was. In the original transformer paper from 2017, they used post-norm, meaning the data would pass through the attention mechanism, get added to the residual stream, and then the whole sum would be normalized.
And normalization just means mathematically scaling the numbers so they don't get too wildly big or too vanishingly small, just keeping them in a healthy, predictable range.
Correct. But post-norm turned out to be incredibly unstable when you tried to train really massive models with billions of parameters. The gradients would explode. So the industry universally shifted to pre-norm.
Okay, and pre-norm means?
In a pre-norm architecture, you normalize the data before it goes into the attention block or the multi-layer perceptron block.
Okay, so the transformation block gets nice, clean, normalized data. What's the problem with that?
The problem is the residual highway itself. You are normalizing the data before the transformation, but then you are adding the output of that transformation back into the raw, unnormalized residual stream. And you do this layer after layer after layer. You're just adding.
It's the snowball rolling down the hill.
Exactly. At layer 1, the residual stream is just the token embedding. It's a small snowball. But by layer 50, the residual stream is the sum of 50 different layer outputs. The mathematical magnitude of that hidden state vector has grown massively.
Wow.
The Kimi paper actually provides the mathematical proof that this hidden state grows at a rate of O of L, meaning it scales linearly with the depth of the network.
Let me make sure I'm visualizing this correctly. Let's say I'm layer 90 in a 100-layer model. My job is to look at the data, perform my attention calculation, and add my specific insight back into the residual stream.
Right, that's your job.
But because of pre-norm, the data I receive to work with is normalized. I do my math, and I output a vector, but the residual stream I have to add my vector into is now this absolute mathematical leviathan. It's a massive boulder.
That is precisely the issue. Your layer 90 output is a handful of snow. You are trying to slap it onto a boulder, rolling at 50 miles an hour. It doesn't change the trajectory of the boulder at all.
So it's basically ignored.
The mathematical reality is that deeper layers are forced to produce increasingly massive, distorted outputs just to have any meaningful influence over that accumulated residual stream.
And what happens to the poor early layers? What happens to, like, layer 2?
Layer 2 is completely buried in the dead center of the boulder. The deeper you go into the network, the more layers are compressed together into a single muddy hidden state vector.
It all just mushes together.
Yes. The paper explicitly points out that each layer only gets to see a single state h sub l minus 1. That one vector conflates and crushes together all earlier layer outputs.
So if layer 5 figures out a crucial piece of syntax, let's say it determines that the word bank in this specific sentence refers to a river bank and not a financial institution.
Okay, good example.
And then layer 80 suddenly needs that specific semantic distinction to predict the next word. Layer 80 can't just reach back and ask layer 5.
It cannot. It only receives the heavily blurred, compressed summary of layers 1 through 79. It is irreversible information loss. And it fundamentally ignores the reality that different layers in a transformer need radically different types of information.
Right, because a transformer isn't just a uniform tube. You have self-attention layers that might desperately need to pull raw context directly from the original token embeddings.
Yeah.
And then you have highly specialized mixture of experts layers that might only care about the highly processed logical deduction from the single layer immediately preceding them.
But under the standard residual architecture, they both receive the exact same rigidly aggregated, muddy state. They have absolutely no choice. The routing is completely blunt.
I remember reading studies a few years ago showing that you could literally just prune away 20 or 30% of the layers in a fully trained LLM, and the model would still perform almost identically.
I remember those.
At the time, people thought that meant the model was just incredibly robust.
It wasn't robustness. It was redundancy caused by inefficiency. The layers weren't actually communicating effectively. They were just repeatedly guessing based on the same muddy summary. Because the routing was so blunt, many layers were essentially trapped, unable to contribute anything unique that wouldn't just be immediately drowned out.
Okay, so if standard residuals compress everything into one muddy state over the depth of the network, wait, this sounds incredibly familiar.
Does it?
Yeah, forcing a neural network to compress an entire history of information into a single, fixed-size hidden vector. That is literally what an outdated recurrent neural network, an RNN, used to do over the time dimension, over the sequence of words.
You have hit the nail on the head. That exact realization is the genesis of this entire paper.
Let's unpack this duality, because if you understand how we fixed RNNs, you understand exactly what the Kimi team is doing here. If you go back to, 2014, before transformers existed, we used RNNs or LSTMs to process text. You feed it the first word, it updates its hidden state. You feed it the second word, it updates that same hidden state.
And by the time you feed it the 100th word, the information from the first word has been compressed and overwritten 99 times. The model develops amnesia. It cannot remember the beginning of the paragraph. It's the sequence bottleneck.
And how did we solve the sequence bottleneck?
In 2017, the attention mechanism was introduced. The core insight was, stop forcing the network to compress the entire paragraph into one vector. Keep the vectors for every single word separate.
Ah, so you don't overwrite anything.
Right. When you are processing word 100, allow the network to dynamically look back to attend to the specific vectors for word 1, word 5, word 50. It generates queries, compares them to past keys, and retrieves exactly what it needs.
It solved the time dimension bottleneck completely. But what the Kimi team realized is that while we fixed the horizontal axis, the sequence of tokens, we left the vertical axis, the depth of the layers, operating like an ancient RNN.
That is the time-depth duality. The sequence of layers in a deep residual network suffers from the exact same mathematical information bottleneck as a sequence of tokens in an RNN.
So the solution is shockingly intuitive once you see it. If attention fixed the time sequence, let's use attention to fix the depth sequence.
Exactly.
Which brings us to the Kimi team's proposed architecture. Full attention residuals or full AttnRes?
Yes. Instead of the simple dumb addition of h sub l equals h sub l minus 1 plus whatever, the input to a layer is calculated using softmax attention weights applied across the outputs of all previous layers.
Neural signal check. Here's why this development actually matters at a technical level. We need to be incredibly precise about what kind of attention we're talking about here.
Absolutely. We are explicitly generalizing depth-wise linear attention into depth-wise softmax attention.
Okay, let's break that down for the listener. What do you mean by standard residuals being linear attention? Because I never really thought of them as attention at all.
Right, but if you look at the matrix math of a standard residual connection where you are just adding things up, you can actually rewrite that addition as a form of linear attention where all the attention weights are simply fixed at 1.0.
Oh, wow.
You are equally attending to everything by just dumping it all into the same bucket.
So it's technically attention, it's just really, really dumb attention that can't change its mind.
Correct. What a full AttnRes does is introduce a learned pseudo-query vector for each layer. The paper denotes this as W sub L. It is a D-dimensional vector, where D is the hidden dimension of the model.
So if the model has a hidden dimension of 4096, this pseudo-query is just a list of 4096 numbers.
Yes. And it is a static learned parameter. During the training process, layer 50 learns what kind of information it generally needs to look for to do its specific job. This learned vector, W sub L, acts as the query.
Okay, so it knows what it wants.
Right. The actual dynamic outputs of all the previous layers act as the keys and values. Layer 50 takes its static query, calculates the dot product against all the past layer outputs to see how well they match, and then applies a softmax function.
The softmax function. We are going to talk a lot about softmax today, so let's make sure the mechanics are clear. Softmax takes a bunch of raw scores and turns them into a probability distribution that adds up to exactly 1.0 or 100%.
Correct. So if layer 50 calculates its scores, the softmax function might say, give me 60% of layer 5's output, 30% of layer 49's output, and 10% of the original token embedding. Ignore everything else.
That's extremely picky.
Very. It uses those probabilities to weight the past layers, adds up the perfectly tailored mix, and that becomes the input for layer 50.
It's beautiful. It's selective, content-aware retrieval across the entire vertical stack of the network. But here is where my alarms are going off. If I'm listening to this, I'm thinking, wait, you said the query is a static learned parameter. Why isn't it dynamic? In normal self-attention across words, the query depends on the actual word you were looking at. Why isn't layer 50 generating a fresh query based on what layer 49 just handed it?
That is a brilliant question, and it is the crux of why this architecture is actually viable. Think about it. If the query vector for layer 50 depended dynamically on the output of layer 49, what would happen to the compute timeline?
Oh, I see it. If layer 50 needs layer 49 to finish before it can even generate its own query, you are totally locked into a strict sequential bottleneck. Layer 50 is completely paralyzed until layer 49 is 100% done.
Exactly. You could never parallelize the attention calculation. By making the pseudo-query W sub L a static parameter that is known ahead of time, independent of the current forward computation, you decouple the intention of the layer from the immediate sequential data.
So you know what all the layers are going to ask for before the data even arrives.
Yes. This is a vital design choice for the hardware optimizations we will discuss in a moment.
Okay, but even with static queries, I have to push back hard here. If this concept is so elegant and it perfectly solves the pre-norm dilution snowball, why hasn't everyone been doing this for the last 5 years? We've known about attention since 2017. Has no one seriously tried to slap attention over the layers before?
They have, actually. There have been several academic papers exploring dense routing or layer-wise attention, but they never made it into production models like GPT-4 or Claude.
Why does it create a massive traffic jam in memory? Because looking at every past layer for every current layer sounds computationally catastrophic.
In terms of raw floating point operations on a single GPU, it's actually not that bad. The overhead is negligible. And during training, backpropagation already requires you to save all those historical layer activations anyway so you can calculate the gradients.
So if I'm just training a tiny toy model on my single gaming GPU at home, full AttnRes works perfectly.
It works flawlessly. But large language models are not trained on a single gaming GPU. They are trained across massive clusters of thousands of enterprise GPUs, H100s or A100s, using highly complex distributed systems. And the absolute bane of distributed systems is communication overhead. Moving data between GPUs is orders of magnitude slower than calculating math inside a single GPU.
Because even with incredibly fast NVLink cables or InfiniBand networks, you are still bound by basic physics and bandwidth limits.
Right, and to train these massive models, we rely heavily on something called pipeline parallelism.
Let's break pipeline parallelism down completely, because this is the invisible wall that killed previous attempts at this architecture.
In pipeline parallelism, you take your massive 100-layer model and you chop it up. You cannot fit it on one GPU. So physical GPU number 1 hosts layers 1 through 10. Physical GPU number 2 hosts layers 11 through 20, and so on down the line.
Like a factory assembly line.
Exactly. In a standard residual network, the assembly line is highly efficient. GPU 1 finishes calculating layer 10. All it has to do is take the single accumulated residual state vector and send it over the network cable to GPU 2. one vector per token. It's a tiny data payload.
But with full attention residuals?
No, right.
Oh, wow. The assembly line completely shatters.
It shatters. Because on GPU2, layer 11 doesn't just want the accumulated summary. It explicitly needs to look at the individual pristine outputs of layer 1, layer 2, layer 3, all the way down to layer 10.
Which means GPU1 has to package up every single layer's output and transmit that massive bundle across the network fabric to GPU2.
And it gets worse. GPU2 processes layers 11 through 20. Then it has to send its data to GPU3. But GPU3 needs everything. So GPU2 has to transmit the outputs of layers 11 through 20, plus the outputs of layers 1 through 10 that it received from GPU1.
It's an avalanche of data. The Kimi paper notes this overhead scales as O of L times D, where L is the total number of layers. By the time you get to the last GPU in the pipeline, you are trying to transmit the entire historical state of the entire network across the interconnect for every single batch.
It would instantly choke the interconnect bandwidth of even the most advanced supercomputer on Earth. The GPUs would spend 99% of their time just waiting for data to arrive over the cables. It is utterly unscalable.
Okay, so we were stuck. We have a theoretically beautiful mathematical solution that cures the fundamental flaw of deep learning, but it is physically impossible to deploy on actual hardware at scale. The cure kills the patient.
Unless you are willing to engineer a highly strategic, scalable compromise. And that is exactly what the Kimi team did with the introduction of Block Attention Residuals.
Block AttnRes. Okay, let's dig into the compromise. If attending to every single individual layer across the network creates an impossible traffic jam, what is the fix?
Grouping. If you can't look at every page of the textbook individually, maybe you can look at incredibly high-quality chapter summaries. The network is partitioned into n blocks.
Let's use concrete numbers. The paper frequently uses n equals 8. So if we have a 64-layer model, we divide it evenly into 8 blocks. Each block contains 8 layers.
Exactly. Inside each block, the layers behave normally. They sum their outputs together using standard residual addition. The snowball rolls down the hill, but only for 8 layers. Once the block is finished, the final accumulated state of those 8 layers forms a single block representation.
It finalizes a chapter summary.
Yes. And when we apply the interblock attention when the network looks backward, the pseudo-query no longer looks at 64 individual layers. It only looks at these 8 block-level summaries.
Plus the token embedding. The paper is extremely explicit about this, and I found it fascinating. The original raw input tokens are always preserved as block 0.
That is a vital detail. By preserving the token embedding as block 0, you ensure that no matter how deep the network gets, every single layer always has direct, unadulterated access to the raw input. If layer 60 suddenly realizes it forgot the first word of the prompt, it doesn't have to guess based on heavily processed logical representations. It just casts its attention weight directly to block 0 and pulls the exact word.
That's incredibly smart. Okay, let's do the math on the data reduction here. We went from having to transmit the history of 64 individual layers down to transmitting just 8 block summaries plus block 0.
The memory and communication overhead drops from O of L times D down to O of N times D. If N is 8, we have reduced the cross-stage communication payload by almost an order of magnitude. We have saved the network cables.
But wait, I have to picture the perspective of a layer stuck inside one of these blocks. Let's say I'm layer 3, which is sitting inside block 4. I haven't finished block 4 yet, so there's no finalized chapter summary. What am I looking at?
It's a hybrid approach. As layer 3 inside block 4, you look backward at the finalized summaries of block 1, block 2, and block 3. That is your interblock history. Plus, you also look at the evolving partial sum of your current block 4. You treat that immediate, unfinalized snowball as one additional source to attend to.
Okay, that makes sense algorithmically, but as a listener, I am immediately skeptical about the resolution loss. If the whole point of this new architecture was to stop compressing data so layers could retrieve highly specific, high-definition details, doesn't squishing 8 distinct layers into one block representation just reintroduce the exact same muddy compression problem we were trying to escape? It feels like we're giving up the magic.
It is the most logical concern to have. And in machine learning, you don't guess the answer to that concern. You run an ablation study. You meticulously test the trade-off. The Kimi team swept the block size across the entire spectrum to see exactly when the magic disappears.
And what did the data show?
The degradation is incredibly, almost surprisingly graceful. They tested a baseline 16-layer model. When they used full AttnRes, meaning a block size of 1, looking at every single layer, the model achieved a validation loss of 1.737.
And validation loss, just as a quick reminder to you listening, is basically the model's error rate. Lower is better. It measures how confused the model is when trying to predict hidden text.
Correct. So the absolute gold standard mathematically perfect routing gave an error of 1.737. Then they grouped the layers into blocks of 4. The error barely budged. It went to 1.746.
That is a tiny penalty.
It is negligible. It even increased the block size to 8, and it achieved almost the exact same performance.
Why? I mean, why doesn't the model care that it's losing the ultra-fine detail of the individual layers?
Because it turns out that selectively accessing distant regions of the network, being able to bridge the gap between layer 50 and layer 5, is fundamentally far more important than having fine-grained, layer-by-layer resolution for the immediate past. A block size of 4 or 8 perfectly captures the macro-level routing benefits. It allows the model to shift major logical concepts across its depth, requiring only a handful of stored hidden states per token to do so.
Okay, so Block AttnRes saves the theory. We reduce the sheer volume of data from O of L times D to O of N times D. But even with that reduction, we are still passing 8 blocks of data down the pipeline instead of just 1. If we are running this on a massive cluster, passing those same 8 blocks over and over again for thousands of batches is still going to cause friction.
Which brings us to the most impressive engineering feat in the paper, the infrastructure optimizations. To actually train this architecture across thousands of GPUs, the Kimi team had to completely rewire how pipeline parallelism handles memory.
Let's unpack the training optimizations. You mentioned the communication cost was still an issue.
Yes. In a naive pipeline setup, even with only 8 blocks, you incur what the paper calls an O of C squared communication cost.
Let me try to visualize why it's squared. If I'm physical GPU number 3 in the pipeline and we're processing multiple micro batches of data, batch 1 comes through and GPU 2 sends me block 1 and block 2, then batch 2 comes through and GPU 2 sends me block 1 and block 2 again.
Exactly. It's totally redundant. The representations for block 1 and 2 for that specific sequence don't change just because a different part of the pipeline is working. But a naive system just retransmits the entire accumulated history every single time a boundary is crossed.
So how do you fix it? You obviously just cache the data locally, right? GP3 just holds on to block 1.
It sounds obvious, but implementing it in a distributed cluster is incredibly complex because of how the GPUs are scheduled. The Kimi team solved this using cross-stage caching, which specifically takes advantage of modern interleaved pipeline schedules, namely the 1F1B schedule.
The 1 forward, 1 backward schedule. Okay, I need you to explain 1F1B and virtual stages to me like I'm 5 years old, because this is where a lot of people get lost in distributed systems math.
I will do my best. Imagine you have a pipeline of 4 physical GPUs. In the old days, GPU 1 would do its forward pass, send the data to 2, wait, 2 sends to 3, waits, 3 sends to 4. 4 finishes, calculates the error, and sends the backward gradient to 3, 3 to 2, 2 to 1.
That sounds terribly inefficient. GPU 1 is just sitting there doing absolutely nothing while 2, 3, and 4 do their work. It's a massive bubble of idle compute time.
Exactly. Those are called pipeline bubbles, and they waste millions of dollars of compute. To fix this, engineers invented interleaving and virtual stages. Instead of assigning a huge contiguous chunk of layers to one GPU, like giving GPU 1 layers 1 through 25, you split the layers into smaller virtual chunks.
So GPU 1 might hold layers 1 through 5, but then it also holds layers 50 through 55.
Precisely. You loop the pipeline back around onto the same physical hardware. So while GPU 1 is waiting for the backward pass of layers 1 through 5 to return, it can actively be processing the forward pass of layers 50 through 55 for a different batch of data. 1 forward pass, 1 backward pass, 1 F1B. It keeps all the physical GPUs constantly busy.
That is incredibly clever. But how does that help with caching our attention blocks?
Because the physical GPU is processing different parts of the network at different times, it sees the data multiple times. If physical GPU 1 is acting as virtual stage A, it receives block 1. It saves block 1 directly into its local HBM, its high bandwidth memory.
So later in the split-second timeline, when that exact same physical GPU 1 is acting as virtual stage E, and it suddenly needs block 1 to do a calculation.
It does not request block 1 over the network cable from another GPU. It just pulls it instantly from its own local memory. It only transmits the incremental blocks, the totally new blocks that have been finalized since the last time the data passed through.
So if it already has block 1 and 2, the previous GPU only sends block 3.
Exactly. This elegant cross-stage caching drops the communication cost entirely. It goes from an exponential O of C squared down to a linear O of P, where P is just the number of physical stages. The redundant transfers are completely eliminated. The network cables can breathe.
That is brilliant systems engineering. It makes training possible. But I am looking at this from a user perspective now. Training is only half the battle. What about inference? When I log into the Kimi app or ChatGPT and I type a prompt, I expect the model to generate tokens instantly. If every single layer has to stop, pull up a cache, and do a complex attention calculation over past blocks, doesn't that slow the token generation down to a crawl? Latency is king in production.
It is the ultimate bottleneck, and it was the second major infrastructure hurdle the Kimi team had to clear. If generation is slow, the architecture is useless commercially. To solve it, they designed what they call the two-phase computation strategy.
Walk me through phase one.
Phase 1 relies entirely on a detail we discussed earlier, the pseudo-query vectors, the W sub L parameters. Do you remember what makes them special?
They are static, learned parameters. They are totally independent of the actual data flowing through the layer. The model knows exactly what query layer 50 is going to ask before layer 50 even turns on.
Precisely. Because those queries are known in advance, the model doesn't have to wait. When the system begins executing a new block, say a block of 8 layers, it already holds the 8 queries it's going to need.
Oh, I see where this is going. If it knows the queries, it can batch them.
Yes. Instead of layer 1 waking up, reading the massive cache block history from the GPU memory, doing its math and going to sleep, and then layer 2 waking up, rereading the exact same massive cache from memory doing its math, which would devour your memory bandwidth.
The model just takes all 8 queries, bundles them together, grabs the historical cache from memory exactly once, and runs a single massive matrix multiplication to get all the interblock attention results simultaneously.
It completely amortizes the memory read cost. It is a textbook optimization. You pay the memory tax once for the entire block, rather than 8 separate times.
Okay, that covers the interblock attention looking backward at the chapter summaries. But what about phase 2? Because inside the block itself, layer 3 fundamentally depends on the output of layer 2. The snowball is actively rolling. You cannot batch that. Layer 3 has to wait for layer 2 to finish its math.
Right. Phase 2 is the sequential intrablock attention. The model computes this step layer by layer using the evolving partial sum. But here is the genius trick. They fuse this sequential intrablock step with an online softmax merge to seamlessly combine it with the parallel results they already got from phase 1.
Online softmax. I've seen this term pop up a lot recently, especially in papers related to flash attention. Let's unpack the math here. Why is online softmax different from normal softmax?
Normally, to calculate a softmax distribution, you have to know every single number in the set before you can do anything. You need to scan all the numbers to find the maximum value, which prevents the exponentials from blowing up and causing a computer error. Then you calculate the exponential of every number, sum them all up to get your denominator, and finally divide each exponential by that denominator to get your percentages.
So it's a multi-pass operation. You have to look at the whole data set twice. Once to find the max and the sum, and again to do the division.
Exactly. But in our phase 2 scenario, we don't have all the numbers yet. The intrablock data is arriving sequentially layer by layer. We have the phase 1 batch results, but the phase 2 results are trickling in.
So how do you calculate a denominator when you don't even know what the final numbers are going to be?
Online softmax uses an algorithmic trick. It maintains a running maximum and a running denominator. As each new piece of data arrives from the sequential phase 2 calculation, the algorithm updates the running max. If the new number is bigger, it mathematically scales down the old running denominator to match the new scale, adds the new exponential, and keeps going.
That is mind-bending.
It is incredibly elegant. It allows the GPU to merge the parallel phase 1 results with the sequential phase 2 results dynamically, on the fly, directly in the ultra-fast SRAM registers of the GPU, without ever having to write the intermediate steps out to the slower main memory.
Because memory I/O reading and writing to the VRAM is what actually slows down LLM inference, not the math itself.
Exactly. Because this online softmax merge is element-wise, it naturally admits kernel fusion with surrounding operations. The I/O footprint remains tiny. Because of these two phases, the batched read and the fused online softmax, the end-to-end inference latency overhead of Block AttnRes is incredibly low.
How low? Like, give me a number.
Less than 2% compared to standard dumb residual addition.
Yeah. Less than a 2% speed penalty to fundamentally upgrade the entire routing architecture of the model, that is a massive win. But wait, there is one more inference bottleneck the paper talks about: long context pre-filling.
Yes. When you upload a massive document, say a 128,000 token PDF to an LLM, the model has to pre-fill or read that entire document before it can generate a single word of response.
Then during that pre-fill, if we are using Block AttnRes, the model has to generate and store the block representations for all 128,000 tokens so it can attend to them later.
And that takes memory. A lot of memory.
Hmm.
The paper explicitly states that without optimization, storing the block caches for a 128K sequence would devour 15 gigabytes of GPU VRAM per sequence.
15 gigabytes just for the cache. If you were running a server with an 80 gigabyte GPU, you could only handle a few concurrent users before the server crashes out of memory.
It would be commercially unviable for long context tasks.
So how did they shrink it?
They utilize sequence-sharded prefilling across tensor parallel devices.
Let's break that down. Tensor parallelism is different from the pipeline parallelism we talked about earlier.
Yes, in pipeline parallelism, you slice the model horizontally different layers on different GPUs. In tensor parallelism, you slice the model vertically. You take a single massive matrix multiplication inside a single layer, chop the matrix into pieces, and have multiple GPUs calculate the pieces simultaneously, then combine the answers.
It's like having 4 chefs chop the same pile of vegetables so it gets done 4 times faster.
Exactly. Because tensor parallelism inherently requires multiple GPUs working on the exact same token at the exact same time, the Kimi team realized they could distribute the massive 15 gigabyte cache across those multiple GPUs. They shard the sequence.
Meaning GPU A holds the block cache for tokens 1 through 30,000. GPU B holds tokens 30,000 through 60,000.
Precisely. By sharding the representations across the tensor parallel cluster, that memory footprint plummets from 15 gigabytes down to 1.9 gigabytes per device.
That's a huge drop.
And they went further. If they applied chunked prefilling on top of that, where they process the prompt in smaller chunks rather than all at once, the peak memory usage drops down to 0.3 gigabytes.
From 15 gigabytes to 0.3 gigabytes, they completely neutralized the memory bottleneck.
They systematically hunted down every single hardware limitation that prevented depth-wise attention and engineered a bypass.
Okay, so the theoretical math is sound, and the infrastructure engineering proves we can actually run it without burning down the data center. But all of this complexity, the caching, the online softmax, the tensor sharding it, is only worth it if the model actually learns better. Let's move into the empirical proof, the hard data. The Kimi team didn't just write a theory paper. They ran massive scaling law experiments.
And this is where the theoretical elegance translates into undeniable empirical superiority. They plotted compute versus validation loss using the standard power law equation. L equals A times C to the negative alpha.
Let's demystify that equation for a second. L is the loss, the error rate. C is the compute budget, how many billions of calculations you let the GPU run. The equation basically just says, the more compute you throw at a model, the lower its error gets, following a predictable curving slope.
Right. It's the iron law of modern AI scaling. They tested 5 different model sizes, scaling up to over 500 million parameters for these initial tests, and trained both standard models and Block AttnRes models.
And what did the curves look like?
The Block AttnRes model consistently outperformed the pre-norm baseline across every single compute budget. The 2 curves run completely parallel to each other, but the AttnRes curve is shifted significantly lower on the error axis.
I want to highlight the specific compute equivalence from the paper because this number is the whole ball game for AI companies. The paper notes that at 5.6 PFLOPs, days of compute.
PFLOP's days being a measurement of how many quadrillions of floating point operations the supercomputer ran over a 24-hour period.
Right. At that specific massive compute budget, the Block AttnRes model achieves a validation loss that the baseline model can only achieve if you give it 1.25 times more compute.
That is a 25% compute efficiency gain simply by changing how the residual stream is routed. Let that sink in. In an era where a state-of-the-art training run on a cluster of H100s costs tens of millions of dollars and takes months of constant power draw, a 25% efficiency gain is staggering. It means you can reach GPT-4 level performance using 25% fewer GPUs, or reach GPT-5 level performance in 25% less time.
It's an economic earthquake. So armed with the scaling law, they didn't stop at 500 million parameters. They decided to prove it at the big leagues. They built the Kimi linear 48B model.
Yes, 48 billion total parameters. It utilizes a mixture of experts design, meaning only about 3 billion parameters are actually activated per forward pass, which makes it highly efficient to run. And they trained it on 1.4 trillion tokens.
This isn't a toy model in a sandbox. This is a state-of-the-art scale pre-training run.
Absolutely. And because they had this massive model, they could finally look deeply under the hood and see how the training dynamics actually changed compared to the broken baseline. Let's go back to our core problem, the pre-norm dilution. The runaway boulder rolling down the hill. What happened to it?
Did Block AttnRes actually cure it?
It was completely cured. The paper includes charts graphing the mathematical magnitude of the hidden states as you move deeper into the layers. In the baseline model, the graph just goes up monotonically. It's a straight diagonal line ascending into the sky. The deeper you go, the more massive and distorted the data becomes.
And the AttnRes model.
The output magnitudes remain strictly bounded. They do not grow to infinity. Instead, they form a beautiful periodic pattern that resets at the boundaries of every single block.
Oh, because at the end of the block, the attention mechanism selectively pulls what it wants and creates a clean, weighted summary rather than just blindly dumping the new data on top of the old pile.
Exactly. The selective aggregation at the block boundaries acts as a pressure release valve. The accumulation resets. This means deeper layers are no longer forced to produce insanely massive outputs just to be heard over the noise. They can output normal, healthy numbers, and the attention mechanism will smoothly retrieve them.
If the forward pass is healed, what about the backward pass, the gradients, the learning signal?
They heal too.
Yeah.
In the baseline model, because of the rigid accumulation, the gradients become disproportionately massive in the early layers, completely throwing off the learning balance. But with AttnRes, the gradient magnitudes became beautifully uniformly distributed across the entire depth of the network.
But why does softmax attention create uniform learning?
Because the softmax weights create a strictly competitive environment for probability mass. If layer 50 decides it really needs data from layer 10, it assigns a high probability to layer 10. During backpropagation, the gradient flows exactly proportional to that probability. The network dynamically chooses where to route the learning signal based on who actually helps solve the problem, rather than just indiscriminately piling the signal at the beginning of the network.
It's a meritocracy of information. Okay, so the internal dynamics are mathematically much healthier. But what about the downstream benchmarks? Does a healthier internal dynamic actually make the model smarter when a user asks it a question?
The benchmark jumps are highly specific and very telling.
Let me rattle off some of the improvements compared to a baseline model trained with the exact same budget. GPQA-Diamond up 7.5 points. HumanEval for coding up 3.1 points. Minerva Math up 3.6 points.
Those are not small bumps. In the current LLM landscape, gaining 7.5 points on GPQA is a massive leap.
Right.
For context, GPQA-Diamond is a dataset of incredibly difficult PhD-level questions in physics, chemistry, and biology. Questions so hard that even expert human scientists get them wrong if they don't have access to the internet. So I have to ask you, why? Why did these specific tasks, coding, math, PhD physics, see such massive leaps compared to, say, basic trivia recall, which only saw minor bumps?
If we connect this back to the broader architectural picture, it makes perfect logical sense. What do physics, math, and coding have in common? They are fundamentally compositional tasks. They require rigorous multi-step reasoning.
Meaning you can't just memorize the answer. You have to follow a chain of logic.
Precisely. To solve a complex calculus problem, layer 10 of the network might calculate a crucial subformula or identify a specific variable dependency. Then, 30 layers later, layer 40 realizes it needs to apply a theorem to that exact specific subformula to get the final answer.
In a standard baseline model, by the time we reach layer 40, layer 10's pristine subformula has been muddied, blurred, and averaged, together with the outputs of layers 11 through 39. Layer 40 is trying to read a smudged chalkboard.
But with attention residuals.
Layer 40 can explicitly fire its static query, scan the historical blocks, retrieve the exact pristine logical step calculated by layer 10, and pull it cleanly forward into the present. It explicitly retrieves specific logical states. Multi-step reasoning benefits exponentially when the network can explicitly route precise mathematical logic across its depth without degradation.
That is fascinating. The model isn't just learning how to do math. The architecture allows it to organize its own internal thoughts to solve the math without losing its train of thought.
Exactly. It maintains logical coherence over depth.
Which perfectly sets up the final major area of the paper. Because if you change how a model thinks, you inevitably change what shape the model wants to be. The performance is undeniably better, but the paper also reveals that AttnRes fundamentally upends how we should design the shape of future neural networks.
To figure out exactly why the architecture behaves this way, they conducted extensive ablation studies on the microcomponent design.
Let's hit a few of the technical choices. Earlier we talked about softmax. The paper explicitly states they tested sigmoid gating instead of softmax, and the performance degraded. If I'm an engineer, sigmoid seems easier. It just squashes numbers between 0 and 1 independently. Why did softmax win?
It comes down to competitive normalization. With a sigmoid function, layer 50 could theoretically look at the past 50 layers and say, yeah, give me 90% of layer 1, 80% of layer 2, 95% of layer 3. It can just vaguely upweight everything if it feels like it. It's not forced to make a hard choice.
It's greedy.
Yes, but softmax is zero-sum. The probabilities must sum to exactly 1.0. If layer 50 wants to give 50% of its attention to layer 10, it has to steal that 50% away from everyone else. Softmax enforces competitive scarcity. It forces the network to make sharper, highly deliberate selections about which past layer is most important. It prevents the network from getting lazy and just averaging everything together, which is the exact problem we are trying to escape.
That makes total sense. Force the model to be decisive. What about RMS norm on the keys? The paper highlights that applying root mean square normalization to the previous layer outputs before running the attention dot product is critical. Why?
To prevent bullying.
Bullying.
Yes, mathematical bullying. Remember that our block representations are the accumulated sums of 8 different layers. Depending on what those layers were doing, the raw magnitude, the sheer size of the numbers in block 2 might be naturally much larger than the numbers in block 5.
So block 2 is just mathematically louder.
Exactly. If you don't normalize those blocks before you run the softmax calculation, block 2 will completely dominate the attention weights simply by being louder, not necessarily because its information is actually more relevant to the query.
The loudest voice in the room gets all the attention, even if it's saying nothing useful.
Precisely. RMS norm scales all the block representations down to a level playing field. It ensures that when the softmax makes its competitive choice, it is choosing based on the actual direction and semantic content of the vectors, not just their raw volume.
It's a beautifully tightly engineered system. Now, I want to talk about the controlled capacity reallocation study, because this data completely blew my mind. The Kimi team asked a very practical question. Let's say you have a fixed compute budget and a strict limit on parameters. How do you shape your model? Do you make it wide, lots of attention heads, a massive embedding dimension? Or do you make it deep and narrow with hundreds of tiny layers?
The classic width versus depth trade-off. It has dictated transformer design for 7 years.
Right. And if you look at the heat map data in the report, for the optimal baseline model using standard residuals, the optimal shape was relatively wide. The ratio of the model dimension to the number of blocks was around 60.
That aligns with conventional wisdom.
But with AttnRes, the optimal shape shifted dramatically. It shifted away from width and heavily toward depth. The optimal ratio dropped to around 45, deeper and narrower.
This is a profound finding for the future of AI scaling. For years, conventional transformer heuristics leaned toward wider models because scaling the depth eventually hit a wall of diminishing returns.
Because of the pre-norm dilution snowball, if adding more layers just makes the residual stream muddier and destroys the early signals, why bother adding more layers? Just make the existing layers wider so they can process more at once.
Exactly. The depth dimension was toxic past a certain point. But because attention residuals completely cures that dilution and provides pristine routing, it makes the depth dimension incredibly efficient.
So the model actively thrives when given more depth to exploit. It completely upends the conventional wisdom of scaling.
If the network can dynamically route information across layers without losing signal, it prefers a deeper sequence of transformations. It wants more sequential steps of reasoning. It is telling us, if you give me clear memory, I would rather think through this problem in 100 small logical steps than try to compute it in 20 massive complicated steps.
That is going to change how every open source lab designs their next architecture. Okay, let's close by trying to visualize what this deeper, highly connected model is actually doing inside. The paper includes incredible heat maps of the learned depth-wise attention weights. We can literally see where the layers are looking during a forward pass. When you look at those heat maps, what jumps out at you?
2 major phenomena are immediately apparent. The first is what we call preserved locality.
Meaning layers generally just look at what just happened right before them.
Yes, if you look at the diagonal of the heat map, it is very dark. The highest attention weights are almost always focused on the immediate predecessor block.
That's reassuring, honestly. It means the model hasn't devolved into total random chaos. The standard sequential step-by-step processing of a neural network remains the primary dominant pathway for information.
But the second phenomenon is where the magic happens. Explicit skip connections. While the diagonal is dark, there are highly specific, strong off-diagonal concentrations of attention.
Give me an example of that.
The most prominent example is that later layers in the deep network frequently cast very high attention weights all the way back to block 0, the original token embedding.
They are double-checking the raw input.
Precisely. They're refreshing their context directly from the source, bypassing 50 layers of processing to make sure they haven't drifted away from the user's actual prompt. Furthermore, the heat maps show a fascinating divergence between layer types. Pre-attention layers, the parts of the network that handle routing sequence context, maintain much broader receptive fields. They cast their attention across a wide variety of past blocks.
While the pre-MLP layers, the multi-layer perceptrons that act as the feed-forward logic gates,
The MLPs are much more narrowly focused. They mostly just look at their immediate predecessors.
so the attention layers are acting as global routers, scanning the whole historical depth to gather context, while the MLPs are acting as localized logical processors, chewing on exactly what was just handed to them.
Exactly. The network naturally learns to specialize its depth-wise routing based on the specific mathematical computation it is about to perform.
So if I synthesize all of this, the model is essentially building its own custom nervous system on the fly. We give it a blank grid of blocks, and during training, it decides which organs, which layers need to talk directly to each other. It forms these complex, dynamic, bypass synapses that completely overwrite the rigid, linear, sequential structure we originally programmed into the PyTorch code.
That is a highly accurate and incredibly exciting way to visualize it. The architecture is optimizing its own internal topology based on the rigorous demands of the data.
Wow. Okay, let's pull back and briefly recap the journey we've been on today. We started by looking at a fundamental flaw: how standard residual connections, the foundational workhorse of modern AI, actually trap and dilute crucial information in an ever-growing, muddy snowball of pre-norm accumulation.
Right. And we saw how recognizing the formal mathematical duality between sequence processing and depth processing inspired the Kimi team to introduce attention residuals.
Mm.
By deploying learned dynamic softmax routing, they unlock that trapped information.
And we explored the immense real-world infrastructure engineering required to make it work, how Block AttnRes grouping, cross-stage caching on 1F1B schedules, online softmax fusion, and tensor parallel sharding neutralized the massive memory and pipeline bottlenecks, making this theoretically beautiful idea a deployable reality that yields huge gains in multi-step reasoning.
It is a true masterclass in full-stack AI research, bridging the gap from elegant theoretical math to gritty hardware infrastructure.
It really is. And it leaves me with a final, slightly provocative thought to ponder, something that builds on this source material but pushes us to look at the horizon.
What is that?
Well, if layers can now dynamically attend to any previous layer using learned queries, and if the model empirically thrives on deeper, narrower structures because it can freely jump around, does the strict sequential linear order of layers even matter anymore?
That is the ultimate question, isn't it?
Right. Are we moving toward a future where a neural network isn't a stacked tower of linear blocks at all? What if future architectures are just a fluid, unstructured graph of compute nodes, dynamically routing information across time and depth simultaneously, firing whenever and wherever the data demands it?
If depth-wise attention fully replaces strict recurrence, the very concept of layer 5 versus layer 50 might just dissolve into a continuous, non-linear field of computation.
Architectural muddy waters indeed, but in a totally new, intentionally designed, and incredibly exciting way. That is all the time we have for today's deep dive. Remember to head over to neuralintel.org and find us on YouTube, Apple Podcasts, and Spotify. We genuinely want to hear from you. Hit the comments and share your thoughts on how dynamic, depth-wise attention might impact the next generation of open-source models. Will the next iteration of Llama or DeepSeek adopt Block AttnRes? Let us know what you think.
Thank you for taking this deep dive with us.
You know, we started today by talking about a broken X-ray machine, a murky diagnostic landscape where early signals just get buried under an accumulated boulder. But with attention residuals, it feels like we finally upgraded the imaging tech. The landscape isn't muddy anymore. It's a glowing, highly articulate web of dynamic connections. And for the first time in a long time, we can see exactly where the signal is going. Catch you next time on The Deep Dive. Sign off from the Neural Intel podcast.